So, welcome back to the second session of today. The conference dedicated to Sergio. It's really a pleasure to be here. I've never been a student or a collaborator of Sergio, but really he had a great influence on all the, community of statistical physics in Italy and outside. So it's really a pleasure to be here. The first talk of today is by Professor Jürg Fröhlich, and please.
Well, thank you for inviting me to this meeting in honor of Sergio Caracciolo. Sergio was my first postdoc when I was still working in the Paris area, and he was already very familiar with using big computers to do simulations. And so we did a project on simulating self-avoiding walk. And then I thought it was actually a nice algorithm, but then afterwards a famous philosopher stepped in and said that our estimates of accuracy were not exactly very reliable. And so the philosopher and Sergio then did a more serious job about these self-avoiding walks. Of course, it had something to do with the triviality problem of quantum of pi to the fourth. So today I'm not going to talk about field theory. In fact, I'm not so interested anymore in field theory. So I'm more interested in quantum mechanics, and I will tell you some relatively recent results about quantum mechanics. I would actually like to talk about some of the fundamental problems, but I think that's not possible in a short talk like that. So I will do something that is not particularly controversial, and it has a good tradition in Italy, as we will see. So, here, the work I'm going to focus on what is in recent papers with Tristan Benoit from Toulouse and Martin Fraas, who is in the US in UC Davis. But of course, other people have also been involved along the lines. And so I will start with a few comments on the foundations of quantum mechanics. This will be cut short so that the talk fits into this relatively short period of 45 minutes. Then I will make a few remarks about indirect measurements in quantum mechanics. Most measurements done in the real world are indirect measurements. So I will give an example later on. And then I will apply the general ideas to a concrete problem, namely, why do charged particles propagating in a cavity trace out tracks when you shine light into the cavity? While if you don't do that, if the cavity is perfectly dark, they behave in a wave-like manner. We would like to understand the details of this phenomenon. Then I will offer a few conclusions. Here is something Dirac emphasized. Incidentally, the Feynman path integral should really be called the Dirac path integral, because he's the one who invented path integrals, not Feynman. And he said that the interpretation of quantum mechanics has been dealt with by many authors, and I do not want to discuss it here. I want to deal with more fundamental things. This shows that he was a very intelligent man, because the discussion about the interpretations has led to an absolutely enormous confusion that is still going on. So, a few comments about foundations. Of course, the entire talk touches upon foundational problems in quantum mechanics. I think this is a subject that ought to occupy center stage of contemporary theoretical physics, because in 3 years from now, we will celebrate 100 years of matrix mechanics. And if you look at the literature, the confusion about what the theory is and means is as big as it was always. And I think that's an intellectual scandal that should be removed. So, I will not deal with this problem although I have written papers about it, but it would take a little too much time. In any event, we have to do better than what most people are doing in that so-called community of quantum foundations. So here would be a few remarks about fundamental questions about quantum mechanics, but I will skip them so that I will not run over time. In the question session, if you want to know more about it, I'd be happy to make a few remarks. So let's go and discuss indirect measurements in quantum mechanics. Why is this so important? For example, if I consider the retinas of my eyes as detectors, these detectors catch photons. Every photon carries extremely little information, but if I let the long stream of photons hit my retinas, I can identify the friendly face of Sergio Caracciolo. It's a completely indirect measurement. And so we have to understand how to model indirect measurements in physics because they are omnipresent. So, of course, measurements in physics, in the end, the result of a measurement should always be communicable in classical language. And so this is why I talk about the classical periphery of quantum mechanics, which is reached whenever you do measurements and talk about them. So the idea of the indirect measurement, you could say, is probably due to Plato in his allegory of the cave. And I'm not sure that we have learned much more since then, but I will try and see. So, what's an indirect measurement? You send many probes to a system that you're interested in. The states of these probes, for example, photons or neutrons or electrons, will entangle with the state of the system you're interested in. And then when the probes leave the vicinity of the system, they're subjected to a projective measurement. And if you have a long sequence of probes, then from the results of these projective measurements, you can reconstruct some properties of the state of the system. That's the idea of the indirect measurement. If you have a good theory of projective measurements, then the general theory of indirect measurements is very well developed. It goes back in quantum mechanics, it goes back to people like Krauss and Maassen and Kümmerer and various other people. Now, I will apply this theory. I will not say very much about the general theory. I will apply it to a concrete example, which has the following history. At the 1927 Solvay conference, in a famous debate with Bohr and Born, the problem of the classical periphery, in particular of the problem of these particle tracks, was raised by Einstein. Born sketched an insightful answer due to Heisenberg to explain why quantum particles can both behave like waves and like basically classical point particles. This problem was later studied by Charles Darwin, who was, I think, the grandson of Charles Darwin, and who was a pretty good British physicist, and then was taken up by Neville Mott. But I think the Darwin papers are in some sense more interesting. In recent times, this problem became very popular in Italy. In particular, Rodolfo Figari and Alessandro Tetta have written a very nice little book about this problem with a wonderful account of the history. I can recommend it to everybody who is interested in this question. So here are pictures to make the point of what the talk is about. Suppose you have a radioactive ball, perfectly spherically symmetric. You put it into a completely dark cavity, then it starts to decay. It emits alpha particles in S waves. So it's definitely a wave-like phenomenon, and you can test the wave nature of the process by doing refraction experiments at the boundary of the cavity. However, if you fill the cavity with some vapor, for example, or if you shine light into the cavity and then record the reflected light by photon multipliers, then all of a sudden these alpha particles trace out straight lines as if they were classical point particles. So that's on the right picture here. Down here is a somewhat more sophisticated experiment. You have a hard photon, you shoot it towards the a heavy nucleus, and then it does pair creation. So you create an electron and a positron, you put the whole setup into an external magnetic field, and so the electron and the positron curl up in opposite directions. All right, now I would like to move forward, but it doesn't move forward. Ah, now it does. Good. So let's briefly review the quantum mechanics of a charged particle and explain what the semi-classical regime is. So I consider a massive charged particle prepared in an initial state of very high kinetic energy. That's the semi-classical regime. It moves in an external magnetic field, and it is periodically illuminated by laser pulses. The scattered light is assumed to hit detectors, and these detectors click with high probability when a photon arrives. What we want to show is that no matter what exactly the initial state of the charged particle is, the observed approximate particle positions sort of line up along a trajectory that essentially solves a classical Hamiltonian equation of motion. That's what we want to understand. So before I turn on the laser light to do light scattering of the charged particle, I just review a few facts about the quantum mechanics of a single particle. I will do non-relativistic quantum mechanics. The Hilbert space of pure state vectors is simply an L2 space over physical space. The Hamiltonian is a kinetic energy term. Oops, sorry. Yes, now. So kinetic energy plus external potential. So the mass is order 1, E is the electric charge of the particle, A is the vector potential of a time-independent external magnetic field, and V is an external potential. The X is the position operator, and P is the momentum operator. They satisfy the usual commutation relations. I assume, and this is an approximation that is probably extremely good in most circumstances, as long as the particle is not accelerated in a very violent way, that between light scattering events, the state of the particle satisfies the Schrödinger equation. People tend to think that the Schrödinger equation describes the propagation in time, or the evolution in time, of states of quantum mechanical systems. This is, of course, wrong, but it is often a very good approximation. I assume that the initial state of the quantum particle has a very high kinetic energy, namely, as compared to a typical energy of a photon in the laser light that I will use to scatter, to do position measurements. The kinetic energy of the quantum particle is much larger than the typical energy of a photon that scatters off the particle. And this is measured by a parameter epsilon, of which I assume that is very small. So then, of course, since the kinetic energy is high and the particle will move rapidly, it is a good idea to introduce rescaled position and momentum operators. The new momentum operator P hat is square root of epsilon times the old momentum operator, and the new position operator is square root of epsilon times the original position operators. And then the commutation relations between the x hats and the p hats contain an explicit factor of epsilon. And so you see that when epsilon tends to 0, you approach the classical regime. All right, now in order to make this a little more precise, I assume that the external vector potential and the external scalar potential might also depend on epsilon in some ways that are described here. These relations are always true if the vector potential describes a constant external magnetic field, and if the scalar potential is a harmonic potential, then they are automatically satisfied. All right, and now in rescaled, oh no, it doesn't seem, oh, all right, good. So in rescaled variables, the Schrödinger equation for the state of the particle reads as follows: I epsilon time derivative of psi as a function of time t equals h hat applied to psi t. H hat is simply the original Hamiltonian, but now expressed in rescaled momentum and position operators. And we assume that the initial condition for the Schrödinger equation has uncertainties in position and momentum that multiply to a constant times epsilon. Okay. Obviously, when you look at this equation, and remember that the commutation relations of p hat and x hat contain a factor of epsilon, then as epsilon tends to 0, this approaches the classical limit. All right. It is useful for what I'm going to say next to very briefly recapitulate Weyl quantization. This quantum system I'm considering here is, of course, the quantization of a classical Hamiltonian system. The phase space of the Hamiltonian system is called gamma. It's position space plus momentum space. I will only look at three-dimensional examples in the following. Points in phase space will be denoted by Greek letters, psi, zeta, and so on. C of gamma is the space of bounded smooth functions on phase space. We can do Fourier transformation. The Fourier transform of a function little a on phase space is called a tilde and is defined by the usual formula. Omega in the exponent here is the symplectic matrix 0 and the diagonal -1s upstairs and 1 downstairs. So what is Weyl quantization? You have a function A on phase space. You compute its Fourier transform. You multiply the Fourier transform not with this with a plane wave, but with a Weyl operator and integrate over the parameter zeta. That's the quantization of the function A on phase space. The Weyl operator is simply the exponential of I psi hat dot omega zeta. Psi hat consists of the operators x hat and p hat, and zeta is a point in the dual of phase space, and omega is the symplectic matrix. These Weyl operators satisfy certain commutation relations that Weyl figured out. Here they are well known. Obviously, if you take the adjoint of a Weyl operator at the point zeta, you get the Weyl operator at the point minus zeta, and W of 0 is the identity. This implies that if A is a real function on phase space, then its Weyl quantization A hat is a self-adjoint operator. Let's now consider a classical dynamics for this charged particle that leads to a canonical flow phi sub t on phase space. This flow is generated by a classical Hamiltonian vector field with a Hamilton function h. This Hamilton function, little h, is simply the one that after quantization gives rise to the Hamilton operator H hat that we saw before. Now I will use the following theorem from semi-classical analysis, which is really not very hard to prove. It's basically something you can do on a nice sunny afternoon. It says the following: if you multiply the quantization A hat of a function A times the quantization of a function B hat, and subtract from this the product of A times B and then quantize, the error that you make is of order epsilon. It can also, of course, it immediately implies that the commutator between A hat and B hat is of order epsilon. Furthermore, quantization and time evolution commute. If you do the quantum time evolution in the Heisenberg picture of an operator A hat, you get essentially the same thing as if you move the classical function A with the symplectic or canonical flow phi t forward in time and then quantize. The error you make is of order epsilon. This is a Yegerov type theorem. If the Hamiltonian is quadratic in X and P, then in fact, you don't even make an error, as is well known. All right, so you should try to remember these two facts of semi-classical analysis because I'm going to use them in a few minutes from now. Now we have to talk about light scattering and approximate position measurements of charged particles. So there are different ways of doing it, but for concreteness, I have the following situation in mind. Every 2 seconds, a pulse of laser light of photons of energy h bar omega, as I mentioned before, is emitted into a cavity that contains the charged particle. The light scattered by the particle is then caught by an array of photomultipliers. These photomultipliers fire with a positive probability when they are hit by scattered photons. The firing of these photomultipliers represents an actual event, or if you like, a projective measurement that leads to wave function collapse, if you like. What you measure precisely with your photomultipliers is a matter of engineering, but from the measured value, you can reconstruct values of 3 commuting observables that are called capital Q, and the measured values I denote by little q. These measured values of this observable capital Q correspond to the approximate position of the charged particle. Now, you can easily make a model of this light scattering and the firing of photomultipliers and so on, but I don't have time to do that now. So I will just give you the result, which many people actually use as a starting point in such discussions. But the result is the following. Let's suppose rho is the density matrix of the charged particle at some initial time, t0. After tau seconds, yes, then I do a light scattering and the photomultipliers fire. Then I let the particle propagate for tau seconds before the next light pulse is emitted into the cavity. The question is, what is the state of the particle just right after the firing of the photomultipliers corresponding to the point Q in position space, but just before the next light pulse is emitted? And here is a formula. You map the initial state to a new state rho of Q, which of course depends on the value that you measured for the approximate particle position, which is denoted by little q. This is given by applying a certain map phi star sub q to the density matrix rho, and which preserves the positivity of rho, and you normalize such that the trace is again given by 1. This map phase, if you go through model calculations, you find that the map phase star sub q applied to rho is of the form. Well, Liouville evolution of a certain density matrix during a time of length 4, and then a sum over an index alpha, an operator f hat sub q alpha applied to rho and multiplied by the adjoint f sub q alpha hat star. So that's really what describes this map phi star sub q. Q, of course, will be identified with the approximate position of the charged particle. That comes next. These operators f hats of q alpha, I call them amplitudes. They are the quantization of smooth functions f sub q alpha of x on position space that are peaked at some point q. And they should have the following property. If you take the modulus of f sub q alpha squared and integrate it with basically the Lebesgue measure in the cavity and then sum over alpha, you should get 1. That guarantees that the map from rho to integral d nu q phi star sub q applied to rho is a completely positive trace preserving map. Okay. Once more, these amplitudes functions f sub q alpha of x are peaked around the point q with a precision that corresponds basically to the wavelength of the photons that you scatter off the particle. Now you can repeat these approximate position measurements many times, and that leads from the initial state rho naught to a state that depends on the measured values of the approximate positions, and it's simply given by a composition of these maps phi star sub q, and then you normalize such that the trace to 1. Now these normalization factors, I call them now P super n sub epsilon rho naught. They depend on the initial condition, and they depend on the n+1 measured approximate particle positions. These are obviously positive quantities because the maps phi star preserve positivity of the density matrix. Furthermore, when you integrate them over the position spaces with the product measure, you get 1. So in other words, P super n sub epsilon rho naught is a probability density on the n-fold Cartesian product of position space. So it's of some interest to consider an arbitrary value for n. So I introduce a space frac q of arbitrarily long sequences of approximate position measurements by simply taking the Cartesian product of position space over all non-negative integers. Now, because of this relation 20, or also because of the definition of this probability, the maps phi star and the probability density, you immediately verify that these measures P super n sub epsilon rho naught times the product measure here are the marginals of a probability measure on the space of infinitely long tracks. Okay. Now, I should add a few further remarks on approximate position measurements. So the initial state of the particle could be perfectly spherically symmetric, and the detector may also be basically invariant on the spatial rotations. It is therefore a little bit surprising that when you do measurements, you can get measurement results that break the symmetry. This is a very typical feature of indirect measurements if you use many, many probes to measure a certain observable quantity of a system. And this goes, the explanation, you know, is sort of well known nowadays. The point is that the states of the photons that are scattered off the charged particle are entangled with the state of the particle. They depend on the position operator x hat of the charged particle. If you let a large number of photons be scattered by the particle and then hit the photon multipliers, this large sequence of scattered photons leads to a measurement, to an unambiguous value for the observable Q. And this value I denote by a little q, and it has no reason to be equal to 0. It has no reason to preserve the spherical symmetry. This is a phenomenon that in recent times has been called purification. I think the first good analysis of this phenomenon can be found in papers of Maassen and Kummer. It was then rediscovered, for example, by Boer and Bernard in their analysis of the Arroche-Raymond experiment, and probably by many other people too. It has something to do with what people call the non-locality of quantum mechanics. So just to remember, if you scatter a large number of probes off a system, then the sequence of measurements can lead to a result that breaks a certain symmetry of the system. That's what happens. So let's now let's now apply semi-classical analysis to sort of understand what repeated approximate position measurements have to do with classical particle tracks. So I remind you that phi sub t is the canonical flow of a classical particle with the Hamilton function that corresponds to the Hamilton operator of the quantum particle. Let me denote by psi the initial condition of a phase space trajectory, and by psi sub j the point in phase space that you obtain after time j times tau. Let d mu epsilon be the Wigner distribution of the initial state of the quantum particle. I choose a sequence of initial states of the quantum particle to depend on the parameter epsilon in such a way that when epsilon approaches 0, the Wigner distributions of these density matrices approach a positive probability measure d mu naught on phase space. It is important to emphasize that the limiting measure can be positive because the Wigner distributions are, of course, usually not positive. Now we can use the insights that were summarized in the semi-classical theorem that I showed, namely the commutators of Weyl quantizations of functions on phase space are of order epsilon, and the time evolution and quantization commute up to errors of order epsilon. If you use these results, you find out the following thing, that these quantum probability densities on m+1 tuples of approximate position measurements are given by basically a classical probability density on m+1 tuples of approximate positions up to an error of order epsilon. The proof of this very important relation is really an exercise that I leave to the listener. Not difficult. So what is the limiting, what is this limiting distribution P super n sub rho naught? It is given by simply a product measure integrated, or a product density integrated with the limiting distribution on phase space. So what is the product density? It is given in terms of these amplitude functions that appeared in the definition of the maps phi star sub q. So in order to simplify notations, let us denote the sum of alpha from 1 to n of the modulus squared of f sub q alpha multiplied with d nu q. Let's denote this by d lambda of x and q. So the measures, these classical limiting probability densities multiplied by the product measures are the marginals of a measure dp sub mu naught on the space of infinitely long sequences of position measurements. And this limiting measure is really an exchangeable probability, a convex combination of exchangeable probability measures. So you should try to remember this formula for the limiting probability measure, and you should try to remember that the quantum probabilities are very close to these limiting probabilities defined in terms of these densities P super n sub rho naught. Now, what I want to show next is that from the limiting probability measure, from this wonderful probability measure dp q. Go forward. So if you look at this measure is, it doesn't talk to quantum mechanics. It's completely defined in terms of classical mechanical data, because xj, qj are the position and momentum operator. Xj are the position of variables of a point in phase space that is visited by a classical particle trajectory. The q's are close to these classical positions, but not very close, because these measures d lambda decay around qj. And the question is now, if you have a long sequence of noisy measurements of classical positions, can you reconstruct from these noisy measurements the exact trajectory? So this is obviously a problem that is important for astronomers. If you track, for example, the positions of a planet around the sun, your measurements of the positions are noisy, and the question is, can you reconstruct the exact trajectory of the planet? I don't know exactly how well understood. You probably know whether this problem is well understood. I think it is a relatively difficult problem, except if the dynamics of the particle is simple. So it can basically be this problem of reconstructing exact trajectories from noisy measurements can be solved for quasi-free dynamics, particles in a constant external magnetic field or in a harmonic potential. I sketch how it is solved for free particles. That's the simplest case. So we assume we have points on a classical particle trajectory that differ from each other by a time lapse of length tau. We are interested in reconstructing the initial condition of this trajectory from noisy position measurements. The map from noisy position measurements to initial positions is denoted by psi tilde. And we would like to construct this map psi tilde. So how does this go? Well, the first observation you can do is you assume that psi tilde has already been constructed. You can now consider the image of a measurable set delta in the space of infinitely long approximate positions to an initial condition in phase space. It turns out the measure P sub mu naught of delta is the same as the measure mu naught of lambda. This is some kind of Bond's rule, if you like. Now let's construct the map psi tilde. So this is an exercise in statistics. Let's first consider approximate values of the momentum of such a charged particle. Well, since the particle moves freely, I would imagine the approximate momentum is obtained by taking a difference of two approximate particle positions, dividing by the amount of time that has elapsed, which is tau, and then multiplying by the mass of the particle. Now we consider the sum of these approximate momentum variables from 1 to n and divide by capital N. Then when n tends to infinity, you can appeal to the law of large numbers to show that this becomes the exact initial momentum of the particle. Okay? The central limit theorem tells you that the deviations from the limiting momentum to the approximate momentum variables becomes Gaussian when you rescale by 1/√n, with a variance that is given by this measure d lambda. Now, since we have been able to determine the momentum of the initial momentum of the charged particle, we can try to determine its initial position by subtracting from the approximately measured positions Qn, the distance the particle would have traveled in time n tau. If you sum these variables over little n from 1 to capital N and divide by capital N, then again by some variant of the law of large numbers, this converges to the initial position of the charged particle. Now, finally, why does this help to understand the quantum mechanics problem? It helps because the probability density on approximate position measurements that quantum mechanics predicts is very close to the probability density that I used in this discussion of reconstructing the map psi tilde, this P sub mu naught, which then, of course, implies that apparently, if you take a finite number of approximate position measurements that you have done on a quantum mechanical particle, it determines with an accuracy of order epsilon an initial condition of a classical particle. And these noisy position measurements are, stay within an error. Oops, sorry. They stay within an error of order epsilon from the classical positions. Now, it would be of interest to show that when n becomes large, the quantum mechanical position measurements sort of diffuse around the classical approximate positions with an error that grows like square root of n, basically. This is something that is probably true, but we haven't actually done the analysis. This might be a nice exercise for people who like this problem. So I expect that a very long sequence of noisy position measurements of a quantum particle exhibits some diffusion around the classical positions, with, which goes like, the square root of the number of position measurements you have done. So, upshot, if you have a charged particle with large kinetic energy, you periodically illuminate it by laser pulses, then you find approximate position measurements that line up essentially along a classical particle trajectory. And this is, of course, what the experiments show. All right, now I'm essentially done. Conclusions. So number one of the conclusions I just mentioned, that's to show that the quantum trajectories diffuse around the classical one. Second remark, the quantum mechanics of indirect measurements of the position of a charged particle by bombarding it with a large number of photons is really quite well understood within idealized models. In fact, there are plenty of other examples of a similar kind. I got interested in these matters because of the Nobel Prize by Arroch. The Arroch-Raymond experiment is the following type of experiment. You have a cavity. You fill it with a coherent state of electromagnetic radiation. Then you let Rydberg, highly excited atoms, stream through this cavity. When they are inside the cavity, the internal state starts to precess, but these atoms are out of resonance with the cavity modes, so they neither absorb nor emit photons while traveling through the cavity. Once they have left the cavity, you measure their state projectively, and from the sequence of measurements, you can calculate back. What can you calculate? You would like to calculate something about the state of the electromagnetic field inside the cavity. You find out that long sequences of measurements are compatible with a precise number of photons inside the cavity. This is a little surprising. So I thought that this Nobel Prize was really a good Nobel Prize. I think it required very sophisticated laser technology, and the result was somewhat surprising. Before you think about it, once you understand it, it's not so surprising anymore. The Nobel Prize this year is not quite comparable, except that I think Aspe deserves it. As the other guys, it's a little less clear. Anyway, we have also analyzed an exactly solved model of particle tracks in an earlier paper. But my feeling is always that when you have an exactly solved model, you don't really understand what's going on. You do calculations and in the end something comes out, but you don't understand the basic mechanism. So I prefer the semi-classical analysis. All right, and okay, 4 was that there are many other examples for this phenomenon of purification and so on, and for why we reach a sort of classical dynamics in certain regimes of quantum theory. I want to thank you for your attention. This is a very joyful event, but I feel present times are utterly depressing, and they remind me of the following painting. This painting is from a cathedral in Segovia in Spain. And it seems to me what we are doing is to sort of celebrate, up here without being completely aware of the fact that the tree might fall in the near future. But of course, I hope it's not the case, but I wish that people would more actively demonstrate for the idea that peace will have to be restored as soon as possible. Anyway, thank you for your attention.
Thank you so much for your talk. We have time for a few questions, maybe, Yeri?
Two small questions. So first, how is the dependence of the variance with respect to epsilon? So you said it grows like square root of n?
Yes.
Then the coefficient depends on epsilon, right, or not?
Yes. I'm not totally sure, but I guess what you're referring to.
The previous slide. Previous slide? Yes, there. No, sorry, no, the other one. Yes.
This one.
No, the next one. Next one.
This one.
Next one.
The next slide.
Yes, you said growing like square root of n, which is there is a coefficient depending on epsilon.
Well, here, of course, there should be a coefficient. This coefficient depends on epsilon, obviously.
Yeah, I was asking how.
But it's not, I haven't calculated it. I think you can do a heuristic calculation. That should not be very difficult. But you would actually like to prove that the error sort of grows like square root of n. And I didn't think very much about the problem. It may not be very difficult, but I don't have I cannot tell you how to do it.
Sorry, also another small question. So you don't put the laser, sorry, you don't put the electromagnetic field explicitly in understanding where. So you don't know that
in this last part.
In the talk, there is the electromagnetic field in the.
So the idea is that there is a relatively strong external magnetic field, because then the trajectories bend, and you can, for example, infer what the mass of the particle is and so on. It's treated as a classical external field, but the laser light can be treated quantum mechanically. And there are, this is not a totally easy problem if you want to do a totally realistic model of a charged particle interacting with the quantized electromagnetic field, as my good friend Alessandro Pizzo can explain to you. But you can do idealized models to understand what happens in this scattering, and then you find more or less this formula for the map phi star sub q. It is, we give a little sketch in the paper of how this map phi star of q can be computed, but one could expand it and discuss really a simple model of this. That, I think, is not very difficult.
Okay, so we thank the speaker again.